Hello and welcome back to our series on electrical and computer engineering. Our conversation tonight is about linearity and superposition. Have you ever been in a situation where there are so many people asking things of you that you feel overwhelmed? Your mother, your girlfriend, or your wife, your child, your grandchild, your boss, your secretary, the neighbor across the street. If only you could push a magic button and freeze time, that would be wonderful. Then you could turn on only one of those people and listen to that one carefully. Think what you will do about that request. Turn that person off, turn on the next one, listen to the second one. Think about your response to the second one, and continue doing that, turning off and on everybody around you. And then when you are ready, you unfreeze time, provide all your answers and responses, and come out looking like a champion and smelling of roses. If only, eh? Well, guess what? In electrical engineering, we can do that. We can take a circuit with a number of sources. Each one of them is an input, asking each resistor in the same circuit, hey, I want the voltage to be this, I want the current to be that. Each one of them is saying different things. So what do? We turn off all the sources minus one, let's say source 1. And then we solve the circuit and find what is the contribution of that source to the current in the resistor we are interested in. Then we turn off that source and turn on the next one and solve the circuit again and find what is the current contribution of the second one in the same resistor. And continue doing that for each one of the sources, but only one at a time is active. At the end of that, you guess what we do with the contributions of each one of the sources. You got it right. We add them up. And that sum is the actual total current in that resistor. We can also do that with voltages, but we cannot do that with power. We say we have superimposed the current contributions of each one of the many sources in the circuit in that specific resistor. Superposition. It is possible to do this, to apply superposition to a circuit, because the circuit is a linear system, and that of course needs some explanation that I'll give you during the rest of the video. For now, I think that's enough for an introduction. Are we ready? I'm sure you are. Let's begin.
We have seen that in a resistor, the current is proportional to the voltage applied to it according to Ohm's law. The current I is proportional to the voltage V according to G. G is the conductance of the resistor. In a resistive circuit that has only one source Vs, the voltage in any resistor Vx is proportional to that one voltage source Vs. Check this out. Vx is K times Vs. The coefficient K depends on the values of every resistor in the circuit and the way they are connected to one another. But what happens if there are two sources in the network, V1 and V2? In that case, the voltage in any resistor Vx is given as a linear combination of the values of the two sources, V1 and V2. And in this case, K1 and K2, those are coefficients that depend also on the value of every resistor in the network and the way they are connected to one another. What happens now if there is more than two sources? Let's say we have M voltage sources in the circuit, V1, V2, V3, all the way to Vm. And we have on top of that N current sources, I1, I2, I3, all the way to In. In that case, the voltage in any resistor X depends on each one of those sources according to this linear expression. Check this out. Vx is K1 V1 proportional to the source V1, K2 V2 to the source V2, and so on to each one of the voltage sources according to the coefficients K's, and then proportional G1 I1 to the current source I1 and to the current source I2, etc., according to the coefficients G's. Every K and every G coefficient depend on the value of every resistor and the way they are connected inside the network. When the output to a system depends on every input according to an expression like that, a linear expression, we say that that system is a linear system. In a linear system, we can compute the contribution of each one of the input sources independently of all the other input sources. In a nutshell, we can use superposition. The voltage in the famous resistor X is the sum of the contributions of each one of the sources, V1, V2, and I1, I2, etc. That voltage Vx has all of those contributions from each one of those sources. To compute the contribution of the source V1, this term K1V1, what we do is we make all the sources, V2, etc., and I1, all the other sources equals to 0, and then we solve the circuit. And the voltage in the resistor, Vx, is going to be merely K1V1, the contribution of the source V01. Then we do the same for the second source, V2. We kill all sources minus V2 and solve the circuit and find Vx in that resistor. That's going to be K2V2, the contribution of the second source, and we keep doing that with each one of the sources. At the end, we add up all of those contributions and we get the actual Vx according to the full linear expression. But the question is, okay, in theory, all of that is fine, but how do we make 0 a source? How do we kill a source? If it's a voltage source, let's explore how to kill it. Let's say this source, a 10-volt source between nodes B and A. It's there sitting and guaranteeing that whatever happens, A is higher than B by 10 volts, right? Correct. If we make that source 0, like this, now the source guarantees that whatever happens, there is no voltage difference between A and B. Pretty much like what? Pretty much like a wire between B and A. A fancy word engineers use for a wire like that is a short circuit between B and A. So to kill a voltage source, we just replace it by a wire. That is what we do. To kill a voltage source, we replace it by a wire, a short circuit. And how do we kill a current source? Let's see. We have a current source 3 amps between nodes A and B. That is guaranteeing that that branch has a current of 3 amps. If we zero that source, like so, that source is guaranteeing that whatever happens, there is no current flowing through that branch between B and A. Isn't that the same as if we just cut a hole in that branch? The current in the branch would still be 0. So that is how we kill a current source. We replace it by an open circuit. We just erase it and leave a hole where the source used to be. To kill a current source, just replace it by a hole and an open circuit. That's how. Now we know how to kill a voltage source, replace it by a wire. We know how to kill a current source, replace it by an open circuit, a hole. But we better see this in action. Superposition in a tutorial time with a circuit with 3 sources, 2 voltage sources, 7 volts, and 10 volts, and 1 current source, 9 amps. And what we want to compute by superposition is the current in this 5 ohms resistor. We're going to solve for that current one source at a time, and then we will superimpose. We will add up the 3 contributions. Remember, the first step is to kill all the sources minus 1. Let's begin with a 7-volt source. We're going to kill this 10-volt source, replace it by a wire. We're going to replace this 9-amp source, replace it by a hole, like so. Check it out. The current source is a hole. It is 10-volt source, now it's a wire, and we can solve the circuit. Find the current in the 5-ohm resistor, and that will be the contribution of the 7 volts source alone. How do we find that current? We can find the current in the source, and that current enters a current divider between the 4 ohm resistor and the 5 ohm resistor. What is the current in the source? It's 7 volts divided by the entire resistance seen by the source, right? Correct. And what is that? That is 3 ohms in series with a parallel of 4 and 5. So 7 volts divided by 3 ohms in series with 4 in parallel with 5. Which of course is 4 times 5 divided by 4 plus 5. We have seen that before. And once we have that total current in that source, it enters this current divider between 4 and 5. Multiply that current times the resistance in the other branch 4 and divide it by the sum 4 plus 5. The current in X is the total current in the source multiplied by the resistance in the other branch of the current divider, 4, and divided by the sum 4 plus 5. Let's do that math, and we get 0.596 amps. Or if you do all of that together, you say this is the current in the source multiplied by the current divider, and you get the contribution to the current in the 5 ohm resistor from the source, 7 volts on the left-hand side of the circuit. If we were to use a calculator, of course, there we have 7 volts and the resistance is 3, 4, and 5. The first thing is we click here to put the parallel of 4 and 5, that is 222, add to get the series, and that is the total resistance seen by the source, 522 ohms. Divide 7 by 522, and that 134 amps is the current IS. And now the current divider. 445. Sum 4 and 5, divide 4 by 9. 44% of the current IS will flow through the 5 ohm resistor. Multiply. That is the current contribution in the 5 ohm resistor from the 7 volt source. 3 ways of computing that, but the same result, of course. Now let's do that for the 10 volt source at the top. We leave that up and we kill the 7 volt source, short circuit, and we kill the 9 amp source, open circuit, like so. Short circuit here, open circuit here, and we are to compute this current. Now that current is going to be the contribution to that total current from the 10 volt source on the top. Well, that is just the current in the source. That is 10 volts divided by the total resistance seen by the source, and that is 5 in series with a parallel of 3 and 4, right? Absolutely. 10 volts divided by 5 in series with a parallel of 3 and 4, and that is 1.489 amps. We have 2 contributions already. Now for the third one, the contribution of the 9 amp source. Kill the other sources. Short circuit this one, short circuit the one on the top, like so, and find this current. How am I going to do that? Current divider. 9 amps divided between 5 ohms and the parallel of 3 and 4. 9 amps multiplied by the resistance of this parallel and divided by the sum, like so. 9 amps multiplied by the parallel of 3 and 4 and divided by the sum of 5 with a parallel of 3 and 4. That is 2.298 amps. Now, to find the actual total current in the 5 ohm resistor, you just superimpose the 3 partial values obtained before. The sum is 4.383 amps. That is the actual current in the 5 ohm resistor. We could have done the superposition with voltages as well. However, we cannot do that for power. We can superimpose voltages, we can superimpose currents, but we cannot superimpose power. Why not? Consider there are 2 sources. Each one produces some current and some voltage in a given resistor. The first source produces V1 and I1, and the second source V2 and I2. The actual currents and voltages in that resistor would be the total current I1 plus I2 superposition, and the actual voltage in the resistor would be VT, V1 plus V2. That means that the actual power in that resistor would be the total voltage multiplied by the total current, right? Which when we expand and distribute that, it gets this expression. So you see the actual total power in the resistor is not just V1I1 plus V2I2. And that proves that we cannot superimpose power. And you may be thinking, all of this is crazy. That's preposterous. Why? So you say, there are easier ways of solving a circuit that has 3 sources, and you are definitely and 100% correct. If every source in a circuit has a constant value, I won't do this. Or if every source in the circuit is oscillating with the same frequency, I won't do this. I would just solve the entire circuit with all the sources at the same time, and that is what we're going to do. However, electric and electronic circuits are subject to sources of many different frequencies at the same time, including DC sources. In such a case, which is very realistic, we cannot solve the circuit with all the sources simultaneously. We have to use superposition. In this term, we will deal with transistors, amplifiers in DC, only the biasing. And next term, we will worry with the signals, with the AC signals coming in from amplifiers, from camcorders, from whatever signal source we have. If you liked this video, click on the like button under this window. And that, my dear invisible friends, is all for tonight.